From the last lecture, I started to talk about conformal field theories in 1+1 dimensions and entanglement entropy in conformal field theories. So yes, I will continue on that. So remember this picture we drew yesterday. So this is the plane, complex plane, x plus. So then I will use this notation where x plus iy is z. So there's two coordinates, x and y. I consider another space-time, or just a two-dimensional space, where I use different coordinate, u plus iv, which is w. And then these two spaces are connected by this transformation. Omega is related to z by log z. This lead curve on the complex plane, it's a radial flow. So we're starting from the origin, and then we flow into complex infinity. So that corresponds to these lead curves here. And as I remarked yesterday, this should be thought of as a cylinder. So the blue curve are periodically identified, but lead curve runs from minus infinity to plus infinity. So this direction corresponds to this radial direction in this original complex plane. So in the complex plane, if you follow the evolution along this red curve, it is like you are making your system bigger. Right? So it's a dilatation operation. In this cylinder space-time, if you think of a blue curve represent a space, and the red curve is a time direction, this is the ordinary Hamiltonian evolution of the conformal field theory put on a spatial cylinder. Okay. So I think last time I started to talk about now the evolution, which is orthogonal to this radial evolution, which is called angular evolution. So it's a circular evolution on the complex plane. In the cylinder, it's a periodic evolution along the circumference of the cylinder. So you just exchange the role of space and time. And as it turns out, this is nothing but the entanglement Hamiltonian or Lindner Hamiltonian. So if you start from the right part of the real axis, okay, so x positive, this flow transfer this positive region of the real axis to the negative region. So it is the evolution which relates right half of the space to the left half of the space. So that's the entanglement Hamiltonian. So I think this has various names: entanglement Hamiltonian, Lindner Hamiltonian, or sometimes it is also called modular Hamiltonian. So to have a more understanding of why it is related to the entanglement Hamiltonian, I take the point of view of the Lindner. I take a point of view that this transformation is a transformation which sends you to the accelerated frame, and then I use the physics of Lindner coordinate and en-route temperature, and then I try to relate it to the entanglement. So the way it works is as follows. So we take this transformation again, but I will work with real time instead of imaginary time. So far, this is the Euclidean space, but now I'm talking about Minkowski space. Okay, so that means I analytically continue this imaginary time IV to real time. So I send V to IV. So that changes sine and cosine here into cosh and sine hyperbolic. Okay. Correspondingly, the circular evolution, circular flow, which I drew before, is turned into hyperbolic flow. So it's not closed anymore, but it's open trajectories. Okay. So these trajectories is the world line of particle or observer, which is accelerated. And in this case, acceleration is just 1, which you can, if you change this coordinate transformation slightly, you can also consider particle with more generic values of accelerations. But in this case, it's just 1. So the accelerated observer, as it turns out, it feels the thermal environment, which is called a Entangle effect. Okay, so accelerated observer is in some sense at finite temperature. Okay. So why is it thermal? From the point, so then we try to make a connection with the entanglement Hamiltonian. It's thermal because density matrix for this observer is not pure, which is precisely because the left half and the right half are entangled. But in this coordinate, you don't see the left half. Okay, so you are ignorant to the states living in the left half of this space. So this ignorance means you are actually in the mixed state. That's pretty much the physics of quantum entanglement. This temperature here, which is called Entangle temperature, so it depends on the acceleration parameter. Here it is just 1, but its temperature is given basically just by a acceleration up to the sum factor. So this is kind of baby version of the Hawking temperature, where in the case of Hawking temperature, there's the in the case of Hawking temperature is given by the surface gravity, 1 over g Newton, and times the mass of the black hole. And in the case of black hole, interior and the outside region of the black hole are entangled. So that's how we get the Hawking temperature. But it's very similar. If you think of this region is some sort of horizon, which is called Lindra horizon. Okay. Right. Okay. So that's, I think I didn't quite finish that part yesterday, so I just completed the story. Okay. So any question for this? Okay. So now we could do a variation of this idea. So far, I have been talking about entanglement entropy or entanglement Hamiltonian for the half space, which is semi-infinite, right? So yeah, from here to positive infinity. So the original space is infinite, and I make a partition such that subsystem L or subsystem R or subsystem A is semi-infinite. But how about if I have a subregion which is finite? So to discuss that situation, we slightly modify the previous conformal map. So we use instead this conformal map. Okay, and I just repeat what I did before. These red curves represent the analog of radial evolution, which we did before. So you should think of this as a it's a good analogy is that in the previous conformal map, I'm putting some sort of vortex. So this should be viewed as a in the fluid mechanics language, it is a streamline and the potential line. So there. So if this is a flow out of the vortex, yeah, let's say this is the flow circulating around the vortex. These are the potential line, which is perpendicular to the flow line. But you can now put two vortices, vortex and anti-vortex. Then we get this conformal map we are now talking about. So there's the vortex here and the anti-vortex. Okay. There's a parameter R which controls the separation between vortex and the anti-vortex. And what this conformal map does is, again, to take the complex plane to a cylinder. Okay, once again, this is cylinder. But if you examine the analog of angular flow, so these blue curves, what it does is to take this segment interval from -r to +r. It transfers this interval to its complement. So this part will be transferred to the complement here and there. So that will work to produce the entanglement Hamiltonian for the finite interval. Okay. This Hamiltonian, this conformal map is useful to study properties of the entanglement spectrum for the conformal field theory. First of all, we could basically repeat the exercise we did before to discuss the finite size scaling of the physical Hamiltonian of the conformal field theory. So we can write down the explicit formula for the entanglement Hamiltonian by using this conformal map. We start with the evolution operator on the cylinder along this blue curve. Okay. So that's ordinary conformal field theory Hamiltonian. But you can transform this evolution operator back to the plane to get the explicit expression of the entanglement Hamiltonian. Okay, so it's simply T is the stress energy tensor, but it is basically just Hamiltonian density. So this entanglement Hamiltonian is obtained from the original Hamiltonian density, which is denoted by Tyy. That's because I'm now thinking of y as the time direction. So Tyy is the Hamiltonian density. It's the evolution operator in y direction. But the entanglement Hamiltonian is this Hamiltonian density multiplied by this envelope function, which is x squared minus r squared. Okay, so this is the explicit formula of the entanglement Hamiltonian for conformal field theory for the finite interval of length r. So I would say it's quite rare that we can write down explicit form of the entanglement Hamiltonian, except for the free cases, we had a formula for the entanglement Hamiltonian written in terms of the correlation matrix, real-time correlator. But for generic interacting systems, entanglement Hamiltonian may be something very complicated, or maybe something very non-local. But in this particular example, there's a very nice formula. Okay. So from here, we can also extract the properties of the entanglement spectrum. For example, the level spacing of the entanglement Hamiltonian goes like 1 over log of r, where r is again the separation between these two. So it's the length of the interval. So this should be, of course, contrasted with the finite size scaling of the physical Hamiltonian, where level spacing goes like 1 over L. Okay. Yeah, so that's basically just, if you keep track of this part, how does it, so in this cylinder representation, the length of the cylinder is set by the separation between these 2 points, which is r in the complex coordinate, but the length of the cylinder in this W coordinate is just given by log R. Okay, so that's how this 1 over log R scaling comes, which you can check directly. So once again, I take this SSH model, but I now focus on the critical point where T is equal to T prime. So it's a conformal field theory. That's the simplest non-interacting conformal field theory. And if you plot the eigenvalues of the entanglement spectrum for large enough subsystem size, we could see this log R scaling. Okay. So I think yesterday I plot the eigenvalues of the correlation matrix themselves. To get the entanglement spectrum, you somehow translate that into the actual entanglement spectrum, and this is actual entanglement spectrum, and which scales like a 1 over log of the subsystem size. Okay, this is for free series, and once again, this can be computed from the correlation matrix method. For interacting systems, their numerics, for example, this is for transverse field Ising model at critical point, done by Andreas Rausiri. He observed also the 1 over log L. Here, L is a subsystem size scaling of the entanglement spectrum. Also, from here, it's clear that the spectrum of the entanglement Hamiltonian is related to the physical spectrum of the conformal field theory. It's just the spectrum of the conformal field theory on a finite cylinder. So that means it's not just the level spacing, but we can also match the spectrum, physical spectrum, and the spectrum of the entanglement Hamiltonian. Okay. Right. Okay. Right. So, so as a quick remark, so we talked about analog of angular evolution, which is this blue curve. Okay. So one may ask, what is the what is there anything we could say about analog of radial evolution? So previously, in the previous slide, in the simpler case, there's the angular evolution, which we use to get the finite size scaling of the physical Hamiltonian. But is there anything interesting for the angular? Sorry, so the radial flow, which is red curve in this direction. So it is actually related to something called the sine square deformation of the lattice quantum systems. So if you, once again, do the same exercise, so we take the evolution operator on this cylinder, in this case, not along this red curve, but along blue curve, and then we transform this evolution operator back to the plane. So if you did this for the red curve, we get the entanglement Hamiltonian. But if you do it for blue curve, yeah, sorry. If you do it for the blue curve, you get the entanglement Hamiltonian. But you do it now for the orthogonal direction. So you get the evolution operator, which is inhomogeneous in spatial coordinate. So the spatial direction is now compact, so we call it theta. But in this case, evolution operator is given in terms of a original Hamiltonian density. So if there's no factor here, it's just the ordinary Hamiltonian for the finite circle, but it is now modulated by this factor cosine theta. These are the constant. Okay. So this Hamiltonian has been discussed in the context of DMRG, where DMRG works better for open boundary conditions, as Adrian discussed yesterday. So DMRG is difficult to do it for periodic boundary conditions. So usually we do it for open boundary conditions. But then one may worry about the effect coming from boundaries, right? If we were interested in the bulk properties, so people try to introduce some sort of envelope function which introduce boundary in a very smooth way. So that it's minimize the unwanted effect coming from boundaries. So that's called sine square deformation. So this sine square deformation is actually obtained from radial flow of this conformal map in a natural way. Okay. Anyway, that's just a remark. Right. So far I've been discussing conformal field theory at the critical point. So if there's no question, I will move on to a case where we perturb conformal field theory. Okay. Yeah. So let's now move on. So I add some perturbation to the critical point, and in particular, we may throw away. If this perturbation is relevant, we throw away from the critical point, and in some case, we completely gap the system. Okay, so let's add such perturbation. So we move away from the critical point, and let's see what happens. The previous conformal maps. Okay, so basically, we can still use them, except the system is not invariant anymore. Okay, so the system changes. It's not conformal invariant anymore because of this term. So what it means is, so this S star part is the conformal field theory Hamiltonian or conformal field theory action. So this part is invariant under conformal transformation. This part is not, so it's somehow inconvenient, but you can keep track of how this term transform under this conformal transformation. So let's do this for the for the entanglement entropy for single interval. So if I just repeat the exercise we did for the conformal field theory, this action is transformed into this action by conformal transformation. So S star part doesn't change, of course. It's conformal field theory. But this perturbation part, there's this coupling G, which sets some scale. So this part is not scale invariant. And it basically turned into some form. So it's still there, but in particular, there's this factor which is inhomogeneous in space. In part, this is exponentially growing perturbation. Okay. So since it's exponentially growing to the zeroth order approximation, you can think of this as just like a hard wall. It says somehow hard wall. Okay. The length scale of the hard wall is set by G and the lattice constant, and if you convert this G into the correlation length, the length of the square well potential is log of psi, where psi is the correlation length. Okay, so this is what's happening. So let's see. Right. So there's exponentially growing potential set by this exponential factor. So what it does is that essentially it makes this system finite. And this finite length is set by the correlation length of the system. Okay? So within this approximation, we quickly see that this system looks like free conformal field theory. But the length is not the length of the original system, but the length is just set by this correlation length scaling. Okay. So there are two boundaries. So one is this. Yeah. Sorry. I have to say I'm doing this for the following setup. So I'm thinking about the original system, which is semi-infinite. Okay. So this original system is semi-infinite. So there's a 0 here, which is the boundary of the physical system. But to compute the entanglement entropy, I turn on the, I do the conformal map, then it sets this boundary. Okay. So the entanglement Hamiltonian is given once again by the Hamiltonian of the conformal field theory. But in this case, the length scale is not set by a log of R, where R is the separation between the length of interval, but it's set by the correlation length of the system. Okay. So that one can also check. So once again, I take the SSH Hamiltonian, and I follow the level spacing of the entanglement spectrum. So previously, level spacing changes as a function of interval size, like a log R or log NA in this notation in this picture. But here, it saturates. Level spacing basically saturates. So we see this equally spaced energy spectrum, which is the conformal field theory spectrum, and it doesn't change. For large enough subsystem size, it doesn't change. Okay. We can also see a distinction between two phases in the SSH model. One is the SPT phase, and the other is trivial phase. And as we discussed yesterday, the distinction between two phases shows up as the presence of the zero mode. So in the SPT phase, there is a zero mode. So that means in terms of many body spectrum, every level is doubly degenerate, whereas there's no zero mode in trivial phase. Okay. So that's traced back to the boundary condition, of course, because this part is just like a free conformal field theory, right? And maybe I just trace back to this point here. So we start from the critical point, and I have a possibility to flow into SPT phase or to a trivial phase. So that is the choice you can make here. Depending on how you perturb your system, you can go into two different phases. The choice of the coupling you make here results in the different type of this region, which is a very, very massive region. So that sets some boundary condition to this region, which is approximately described by conformal field theory. Okay, so the type of boundary condition here is completely set by the type of the coupling you make, and accordingly, there's a correspondence between the boundary condition you put here for the conformal field theory and the massive phase you flow into. Okay, so from the point of view of the conformal field theory, different SPT phases, trivial phases, it's just a choice of the boundary condition you make. So if you make a proper boundary condition, you make the spectrum in this region double degenerate. Or maybe if you put the kind of trivial kind of boundary condition, there's no degeneracy, and then you get this kind of spectrum. Okay, right? Yeah, so I want to say a few more words about this. So this line of thinking suggests that there's a correspondence between boundary conditions in conformal field theories and possible SPT phases or trivial phases in gapped phases, which is adjacent to a conformal field theory. So so that is already kind of seen here as a degeneracy in the spectrum. But is it possible to get topological invariant of the SPT phase from the knowledge of the boundary conditions in conformal field theories? So, so remember yesterday I mentioned a topological invariant of SPT phases is a phase which appears, maybe I have it here. So if you remember this equation, this is the action of the symmetry on the virtual space in MPS wave functions. which is different from the, which satisfies the algebra, which is slightly different from the physical symmetry operations because of this phase factor. Right? So this is topological invariant. So the question is, can we get such phase from the knowledge of the boundary conformal field theory? And the answer is yes, and we could do it. So how do we do it? So so there's a common technique in the conformal field theory with boundary, or boundary conformal field theory in short. So the idea is the following. So I have a partition function of the conformal field theory with boundary. Okay. But you can exchange the role of space and time, which we have been playing with. So instead of having a boundary in space, okay, if you make a 90-degree rotation, you exchange a space and time. But in that case, there is the boundary in time. Right? So that simply means that we start from a particular state, okay, which is usually not the ground state, and then you make a time evolution, and then you end up with some particular space. So you're kind of interested in the transition amplitude from one state to the other state. Okay. By this 90-degree rotation, we identify states which are living on the temporal boundary, and that is called the boundary state. Okay. In the original picture, there is a type of boundary you can specify here and there. You can put the different boundary conditions. After 90-degree rotation, you identify different kinds of states. Okay, so different kinds of states represent different kinds of boundary condition in conformal field series, and then there is so this has been called boundary state, and you can construct boundary states for different boundary conditions in boundary conformal field series. So sometimes it's difficult, but people study this problem. I think initially by Cardi and the other people. So we now know not everything, but we know a lot about boundary state in boundary conformal field theory. So once we make this, once you make use of this trick of using states to represent a boundary condition, we can extract this topological invariant appearing here from boundary states. Basically, once you construct a boundary state, you act with symmetry operation, and then you get some phase, which turns out to be nothing but the phase which appears in this symmetry operation in the internal space of matrix product state. Okay. So a few more remarks. So to construct a boundary state, we basically need to solve this equation, which basically says a stress energy tensor T minus stress energy tensor T bar, anti-holomorphic part. So T minus T bar must annihilate this state, which is in the original picture, it's simply saying nothing really flows through the boundary, because that is what the boundary is. So energy must not flow through the boundary. Okay. So by solving that construction, we can solve that state. Okay. The second remark is that this the phase, projective phase we have been talking about is something called a group cohomology phase, or just a group so this phase is classified by something we could call group cohomology, and that has been made use to make a general statement on the classification of SPT phases. So in 1 plus 1D, it's a kind of simplest case. And this phase, the statement is that this phase can be extracted for the SPT phases nearby a conformal field theory. This group cohomology information can be extracted from this consideration. Okay. So the final remark is the following. So far we have been saying, from the point of view of CFT, different gapped phases may be corresponding to different boundary conditions, and different boundary conditions corresponds to different boundary states. Okay. Yeah. So constructing different all set of boundary states is maybe difficult, but at least conceptually, you can make this correspondence between gapped phases and the possible boundary states in conformal field theory. So we can make, so that's, I think, this presentation basically says that, but one can make a step further by conjecturing that this boundary state is actually nothing but the ground state of the gapped phase. Okay, so that's a conjecture, I would say, but you can sort of check. So let me start with this. Yes. So example. So this is the continuum limit of the SSH model, which is a massive Dirac fermion in 1 plus 1 dimensions. So this mass act is basically t minus t prime. Okay, so when t is equal to t prime, you have a critical theory, which is a continuum Dirac fermion. But if you make t not equal to t prime, you add this mass term. So this is a massive theory. So what is the ground state of this Hamiltonian? Well, we know how to solve it. You can check the ground state of this Hamiltonian is given in this form, where this is a Fock vacuum of the fermion system, but there's this factor. And so if you compare this expression with the boundary state in this theory, it precisely agrees with agrees. Okay. More generically, you can ask the following question. So yeah, so conformal boundary states, which is given by solving this equation. So usually this is considered as just a trick. Just we exchange space and time, and B is just a trick to represent the boundary conditions. But B is some state anyway. Okay, so it's not the ground state of the conformal field theory. It's not the ordinary excited state of the conformal field theory, but it's just some state. So we can ask, what is the property of this state? Okay, for example, what is the correlation function? Let's say equal time correlation function of this state. And you quickly discover that correlation function in this state is pretty much very short-ranged. Okay, so there's basically no real space correlations in this state. So that's somehow indicative that it is so in conformal field theory, correlation functions decay like a power law. But for this boundary state, it's not. It's a very short range. So it suggests that it may be the ground state of fully gapped phase, where correlation length is very large or maybe infinite. Okay, so this idea have been explored, for example, by John Cardy to explore the phase diagram of massive perturbed conformal field series. Anyway, so it's not a very rigorous statement. I think up to this point everything is rigorous. But I think there's an interest. I just want to mention this idea of viewing boundary states just as the the ground state of the corresponding massive phase. Okay. Right. Okay, so so if there's no question for this part, I will move on to a different part. Okay. So once again, I will be discussing conformal Fourier series perturbed by some operators. But in this case, I will talk about not the properties of the end point of the RG, but I want to talk about RG flow itself. So there's this C theorem. Okay. So in conformal Fourier theory, a way to characterize there's a convenient number C, which is central charge, that characterizes partially the conformal Fourier theory. So it's like or the parameter for conformal Fourier theory. But how about if we depart from the conformal Fourier theory? Once we perturb conformal Fourier theory, is there any such number? So this idea has been explored first by Zamolodchikov, which I think I put his name in a different slide. But there's something called a Zamolodchikov C function. So that is the function which is the function of the length scale. So it's a function of the RG time. And that function agrees with the central charge at the critical point. So that's the point number one. So in some sense, you may be able to use C function as a alternative of central charge if you are not exactly at the critical point. Okay. Point two, this C function of Zamolodchikov satisfy a very convenient property which monotonically decrease under renormalization group flow. Okay. So with this Zamolodchikov C function, it's somehow, I think I had this good analogy somewhere. So it's an RG flow. So you have a phase diagram, and there's maybe conformal Fourier theory. There may be some flow. So there may be some flow to, let's say, other conformal Fourier series. And then there may be even more RG flow starting from this conformal Fourier series. But in general, we don't know. So this may arise from some computation. But in general, we don't know the idea. If we, let's say, compare two conformal Fourier series, we don't know if we flow into that conformal Fourier series from the other conformal Fourier series or vice versa, what happens. But C function is something like a mountain. So with C function, it gives you like a height. So you have mountains. So with C functions, okay, maybe this is not a good picture. With C function, you have a sense that for a given conformal Fourier series, you always flow into the other conformal Fourier series. So it somehow gives you, I don't know, like height function in the theory space of 1+1 dimensional Fourier theory. Okay, so that's quite important. So original idea of Zamolodchikov didn't mention anything about entanglement entropy. It's something else. But more recently, people realized that entanglement entropy may be also useful to say something about the direction of the renormalization group flow, or even monotonicity of the renormalization group flow. Cassini in 2004 defined something he calls entropic C function. Precise connection to Zamolodchikov C function is not clear, at least not clear to me, but he defined this function. So it's given in terms of the entanglement entropy for the given subregion of length r. So SR is the entanglement entropy. But you take a derivative of this entanglement entropy with respect to the size of the subsystem. Okay? So this is called entropic C function. If you remember the formula S given by C divided by 3 times log R. So at critical point, you can easily check that this function agrees with the central charge. Okay, so that's pretty much like a homological C function. But homological C function monotonically decrease under renormalization group flow. Can we say something like that? So yes, there's some similar property for this entropic C function, which is also monotonically decreased. So this prime is the derivative with respect to R. So that you can show the derivative of entropic C function with respect to the size of the subsystem is always negative. Okay, so that's the monotonicity property of the entropic C function. The proof of this the monotonicity of the entropic C function makes use of the strong subadditivity property of the entanglement entropy, which I listed yesterday and I mentioned as one of the key property of the entanglement entropy. So it's basically you can make use of this strong subadditivity condition to show that entanglement entropy is a concave function. The precise proof given by Cassini made use of physics of relativistic field theory. So that's just very quickly. We consider two regions. So I have a and B, which are overlapping with each other, like this. So A is here, B is here. So there's some overlapping region, and that's precisely. So then we use this strong subadditivity condition. In Lorentz invariant field theory, we can basically Lorentz boost these two regions. You can talk about Lorentz invariant length, which is so if the length of A union B is capital R, and if the length of A intersection B is small r, the Lorentz invariant length of region A and B is just given by square root of R, small r and capital R, and then we use this formula and take this limit. But anyway, I just want to mention the strong subadditivity is crucial to prove the monotonicity of the entropic C function. Okay. Okay. So I think that's pretty much all what I wanted to say for 1 + 1D CFT or perturbed CFTs. So one last comment is what happens for higher dimensions, and I just have one slide for that. So in one-dimensional conformal field series, we mentioned there's the central charge that being quite useful, or maybe even if you go away from the critical point, it's also useful because you can consider C functions, homological for maybe entropic C functions. People have been discussing something like this also for higher dimensions. So this is going to be very quick, unfortunately. But yeah, so for 2 + 1 dimensional conformal field theory, first of all, is there something like a central charge? Well, not in obvious way, because 1 + 1D CFT, in 1 + 1D, central charge appears as an anomaly for the wire scaling. In 2 + 1 dimensional theories or any odd dimensional conformal field theories, there's no such anomaly, which turns out to be true. So from that point of view, there's no analog of central charge in 2 + 1 dimensions. But however, if you consider entanglement entropy, for example, take a disk as a finite disk of radius r as your subsystem, and you just what is the entanglement entropy. And so for generic conformal field theory, there is this area law term proportional to the radius r, or circumference 2 pi r, and there's this sub-leading term, and which turns out to be there and universal, okay, for generic conformal field series. So that is, if you, so I will actually mention topological entanglement entropy in the next in maybe 10 minutes or so. But if you are familiar with topological entanglement entropy, it's somewhat similar to topological entanglement entropy. But this is, such term exists also for conformal field series. I think the distinction is that I think for topological entanglement entropy, it's more insensitive to the shape of subregion than this term f in 2+1 dimensional conformal field series. So in topological entanglement entropy, for example, doesn't care about the cusp. But for conformal field theory, if your subregion has a cusp, this it may be affected. It may affect this term, anyway, there's similar. I think there's similar physics. So this term may be able to label different kinds of conformal field series. Okay, so that's a story at the critical point. So people thought, oh, this may be used as a analog of central charge. We may be able to use this universal constant to distinguish different conformal field theories. Away from the critical point, this function, this part is not the number, a constant number anymore, but it depends on the size of subsystem R. Okay, so pretty much like an entropic C function story. So then, similar to C theorem, there is something called F theorem, which says something about the behavior of this function. I think this was actually first phrased in terms of the partition function of the conformal field theory. The field theory on the 3-sphere, which is called, that's why it is called F. And then people make this theorem first as a conjecture. So we also study this universal properties of the partition function of ON theories or other theories on S3 early on. Okay. So the conjecture, the theorem is basically the same as 1+1D story. So this F, if you compare this function F in the ultraviolet and the infrared of the RG flow, it always decreases in the IR direction. People also define something like a entropic C function, which is called entropic F function now, and it satisfies similar properties. Although it's just some unwanted properties as compared to the C theorem in 1+1 dimension. But anyway, there's something like this in 2+1 dimensions. Okay, just a quick remark. Okay. Okay, so with that, I think I basically switch to a different subject. Now it's a fully gapped topologically ordered phases of matter. Okay, is there any question? All right. Okay, so now I move on to topologically ordered phases. So that's another. That also represents another interesting class of phases in condensed matter. So I think the good example is the fractional quantum Hall liquid realized in for example, 2DEG in the presence of strong magnetic field, or maybe in some frustrated spin systems. So we may have quantum spin liquid topological kind of quantum spin liquid. So these are phases which are, once again, which are not characterized by symmetry breaking paradigm. Once again, we have to look for some indicators or something analogous to other parameters to characterize these topologically ordered phases. For the case of topologically ordered phases, universal properties are basically properties of the excitations in the system, which are called anyons. Okay, so anyons are, I think I give a very brief description of anyons, but that's the exotic particles which obey either fractional or non-abelian statistics. And the braiding properties of these anyons basically characterize the phase. So there's a set of data, like a type of anyons and the type of braidings among anyons and so on and so forth. So they serve as a some sort of order parameter for topologically ordered phases. Okay. So here's a quick summary of the properties of the anyons. So yeah, so like I already said, yeah. So I think in the mathematical term, there's a theory for anyons. That's called the tensor category theory, or unitary modular tensor category theory. But anyway, these are basically the data we want to know for anyons. So particular topologically ordered phases are characterized by these data, and we want to know we want to extract these data from experiment or maybe from numerics or something like that. So what are these data? So we first want to know a set of anyons in your system, and there's a finite number of anyons we want to, a finite number of types of anyons, okay? And for each anyon, they have a notion of a quantum dimension, which is, so I have a particle 1. 1 is a special particle. It's a trivial particle, so that's why we call it 1. But in general, we could have an anyon like a 1, A, B, or all kinds of anyons. And the properties of them so far are unspecified. But the first property I want to specify is the quantum dimension. So each particles, there's a particular dimension associated to them. So this dimension, roughly speaking, roughly measures the non-abelian nature of anyons. So if the quantum dimension is 1, these are abelian anyons. If quantum dimension is larger than 1, we call they are non-abelian anyons. So anyons can fuse with each other. So if you bring two anyons together in space, they create a new they turn into combined or fused new excitations. So there's some rule which we call fusion. So anyons, once again, they have a non-trivial braiding properties, and we can talk about the braiding of anyon among themselves. The braiding of different anyons, or braiding of the same anyon of the same kind. And the braiding of the anyons of the same kind roughly encoded is something we call the T matrix, which is in the particular basis. It's not really the matrix, but it's some sort of like a spin. So it's not really a matrix. If I take since we take usually the basis where T is diagonal, and the diagonal entries is usually called theta. And this roughly corresponds to like a spin of the particle. Since anyons are not fermions or bosons, they may not have a spin statistics relation of the ordinary kind. So there's also another matrix which we call S matrix, and that's roughly encodes the braiding statistics among different kinds of anyons. And there's a formula relating all these quantities this way. Okay. There's only one more quantity which I need to mention, which has nothing to do with the braiding properties of the anion, but it's more like it's related to the properties of the physical edge state. So that is something we call chiral center charge, which is pretty much like the similar to the center charge we discussed in the context of 1 + 1 dimensional conformal field theory, except in the context of here, we are talking about chiral center charge. So it's a center charge for the holomorphic part minus center charge for the anti-holomorphic part. Okay. So the reason I have to specify this number is that there are some phases which share the same braiding properties of anyons, but yet they may be different in the sense that there's no smooth adiabatic path connecting them. Okay. So that happens when the chiral center charge of these two phases are different. Okay. So topological properties might be the same, but they may be still different. So that's why we have to supplement this number. But anyway, we kind of conjecture that properties of 2 + 1D topologically ordered phases are characterized by this set of data S, T, and C. Okay, that's usually something we want to know. So this is abstract, but for example, these numbers or these data can be extracted, let's say in numerics, by looking at ground state degeneracy, degenerate ground state. So as a, well, maybe the zeroth order characterization of the topologically ordered phases, we look at the ground states of the system put on a spatial manifold with non-trivial topology, such as a torus. So then there is the ground state degeneracy, which has nothing to do with symmetry breaking. So that's called ground state, topological ground state degeneracy. It's called topological because once you change the topology of the space, for example, if you change the number of holes in your spatial manifold, the topology changes. Okay, so that's the concept of topological ground state degeneracy. And let's say now we consider ground state degeneracy on a torus. Okay, so we have a set of ground state. And from this degenerate ground state, we can extract this S and T. These are the matrices. That is a kind of the data we want to know to characterize this topologically ordered phases. It can be obtained by changing or adiabatically searing or changing this torus in this way. So you should think of this as a torus where this side and that side and this side and that side, they are all identified. So you have some ground state living in there. But you can adiabatically change the shape of the torus. And then ground state manifold, so the ground state, they undergo some change. And after you make this particular adiabatic process, the original ground, if you started with a particular ground state, it is transformed into linear superposition of other ground states. So there's a way to extract. So these T and S are associated to a particular adiabatic process where you deform your torus. Okay, so that's by doing this adiabatic process, you can extract these S and T matrices. And the claim is that these S and T matrices extracted this way is precisely the S and T matrices which we discussed here. Okay. So from the point of view of the entanglement entropy business we have been studying, yeah, we want to extract such universal data of topologically ordered phases. So that is going to be the last topic. Okay, so how do we extract such data? Well, so idea is once again we look at the entanglement entropy of the system. So for example, we consider topological liquid living on a plane. Okay, and then once again we make a spatial bipartition. So we create a subregion, let's say L, and subregion R, and we trace out part of the system, and then we look at the reduced density matrix. Okay. So the question is, how do we? Yeah. So this can be done numerically, for example. But here I want to present a kind of field theory way of computing this quantity. So how do we compute this quantity? So it can be computed from the field theory point of view in the following way. So first of all, as it turns out, we can write down a expression of the reduced density matrix. So maybe this should be rho sub L. Sorry, I trace out region R. So we are interested in the reduced density matrix for this subregion L. So we have to first, before computing entropies or other quantities, we have to basically get this reduced density matrix. But there's a series of work here listed here basically shows that this reduced density matrix can be written in terms of the edge series of the system, which may be viewed as living on the boundary of this fictitious edge, which you create by making the entanglement cut. It is written in terms of so it is written in terms of this boundary CFT living on the boundary, and it is written in the language of boundary state in conformal field theory. So boundary state I introduced before in the context of 1 plus 1D CFT, but it also shows up in the context of 2 plus 1D topologically ordered phases. Okay, so this is the nice formula which allows you to compute various entanglement related quantities. So this is a very useful formula. So I want to make use of this formula, and just want to show you how you compute entanglement entropy in field theory. Okay. Maybe just a quick remark about the boundary of topologically ordered phases. So I will be interested in the bulk properties of topologically ordered phases, like properties, braiding properties of anyons. So this data is a topological invariant of the system. So we are interested in that. So in topologically ordered phases, in particular the chiral one, it is known that the bulk, if you make a boundary, it supports the gapless edge state, and at the zeroth order level, the very presence of the chiral edge state is the bulk boundary correspondence. So the presence of the edge states says bulk is topological. But since I presented the data characterizing the bulk topological ordered phases, one may wonder, is it possible to extract universal properties of the bulk just from the physics of the boundary? Okay, so that's kind of a more precise version of the bulk boundary correspondence, and yes, that is possible. So the idea is basically as follows. So bulk anyons, which is represented by a star here, it's not the truly local excitations. Particle like anyons, particle like electrons, they are local. It's a fundamental particle as a problem. But anyons, we treat it as like a point particles, but they are emergent excitations. So it's not it's not really the physical electron operator. So once you try to create, it basically disturbs your system. So in particular, anyons, they obey anyonic statistics, which is different from Fermi statistics or Bose statistics. So that's, in some sense, they are mediated with some sort of non-local interactions. So that non-local interaction somehow propagates to the bulk. So if you create anyons, some sort of branch cut or string propagate to the edge, and the edge basically feels the presence of the bulk anyonic excitations. So in more precise terms, what happens is that if you create a bulk quasi-particle or anyon in topological liquid, it changes the boundary condition of the edge mode. Okay? So then we can make since the presence of different kinds of anyons corresponds to different kind of bulk wave functions and the topological degeneracy, there's a correspondence between bulk wave function and the partition function of the edge excitations for a given boundary condition specified by I. Okay? So bulk wave function without boundary, let's say it can live on a torus. So then we extract S and T matrices. In terms of the boundary language, we can consider a space-time torus. So edge is a circle. So this circular region is edge. But if you also consider a imaginary time direction, which is also circle, so together we form a space-time torus, and the partition function of the edge theory, if you consider adiabatic deformation of the space-time torus, they also transform pretty much like the bulk wave function, which transform under adiabatic deformation of the spatial torus. So you can extract from the transformation properties of the space-time partition function in the edge theory, you can also extract this S and also T matrices. And the bulk boundary correspondence says basically S and T matrices extracted from the edge theories must agree with S and T matrices for the bulk wave functions. Okay, so that's the bulk boundary correspondence for physical boundary, but basically something like this also is true for the boundary, virtual boundary created by this entanglement cut. And then this reduced density matrix is written in the language of the virtual edge theory living here. And the precise form of the reduced density matrix is given in terms of the boundary state. Okay. So now I want to make use of this formula and then compute entanglement entropy of topological liquid. Okay. So once again, we start with this condition, which allows you to construct a boundary state. Okay. So that's the first step. And then the solution to this problem is known, and it's given by the linear superposition of this state. So remember, in conformal field series, states are labeled by 3 integers, h, maybe 6 integers, but let's say for the holomorphic part, we care about this h, which basically label a tower of state you're interested in, and within the tower h, there are a set of states which are labeled by n and j. So n is like a level, or like which floor you are living in, and j is the room for a given floor. So there is a degeneracy factor. Okay, but you just take equal superposition of this state, and as it turns out, this solves this equation. Okay, this is a known solution to this equation. So this is the explicit form of the boundary state. And we have to normalize that a little bit. So we introduced this normalization here, which was also here before. Okay, so it's basically given by the the boundary state, but we have to normalize it a little bit. But from here, essentially, we just follow, just pretty much do just a brute force calculation. So the density matrix is given by tracing out part of this boundary state. And yeah, maybe I forgot to mention, but so in this formula, I have 2 degrees of freedom living on near left and the near right, and they have opposite chiralities. And when we trace out R, we trace out the half of the system which is living near this region R. So that is here. We trace out the anti-horomorphic part, and that can be done. And with some more details, this can be represented as just using this formula. And this is just a straightforward calculation to show that power of the radius density matrix, and if you take a trace, it is given by this formula. So here, this matrix S shows up because when we take the limit where length along the entanglement cut is much larger than this regularization epsilon, we have to do S transformations, which I introduced in terms of physical edge state. So this S matrix appears naturally, and then in this limit, only the particular entry of the edge matrix survive. Anyway, so that's some details. But anyway, the point is that once we know the explicit form of the radius density matrix, we can really carry out this calculation of computing entanglement entropy. And the final result is perhaps something you're already familiar with. So let's look at just von Neumann entropy. So this part depends on the circumference of the entanglement boundary divided by this normalization or regularization parameter. So this is the area law term. And so this term is proportional to the chiral central charge. So that is one important data to characterize topological liquid. This part, unfortunately, is not universal, because as you change this regularization parameter, this part will be modified. But anyway, there's a subleading term, which is like this F we just talked about like 10 minutes ago. But this part is related to this S matrix this way. And D is the total quantum dimension, which is listed in the very beginning of the discussion of the topological liquid. So this is total quantum dimension. OK, so this is the so-called topological entanglement entropy. So by topological entanglement entropy, we don't get all data of the topological liquid, but at least we get most dominant information characterizing topological liquid. OK. So I think that's all I prepared. So I presented, what is about this? So so I explored the idea of using entanglement, or maybe the scaling of the entanglement entropy to characterize different phases of matter. And I think it's still ongoing. So if we can fully characterize different phases of matter just by using entanglement, it's an interesting question, and it's still ongoing. But as we have seen, we pick up various universal information just considering the entanglement entropy. So it's a promising idea. Also, it can say something about the structure of the theory space of phase diagram, since it tells us about like a direction of the renormalization group flow. I would also like to mention that something like a physics of space-time and the connection to entanglement in many-body physics. Many people are interested in this idea, and I think today I chose not to talk about this, but But nevertheless, something like this a connection to Lindner Hamiltonian and under temperature is like a baby version of this idea. So entanglement and the space-time property is pretty much related. Okay. Yeah. So yeah, in the context of Lindner, it's a global property of the Lindner coordinate. Since it doesn't cover the whole space, it's basically related to the something about the entanglement from a given subregion. Okay, so that's I think all I want to say. So thank you for your attention.
We have about 10, 12 minutes for questions, discussions. Yeah.
So this RG flow, can it be interpreted as if I'm looking at spin chains, then I go to a large size and then I go to one point, and then if I go to a larger size, then it flows to another?
Yes. Yeah,
okay, so
yeah.
So the previous point is not actually a fixed point, because if you scale for large number of sizes, then you won't actually see scale invariance. It will.
Yeah, yeah. So that's right. So I think small size calculation may be deceiving.
Okay.
And the you can, by going to the larger system, for example, you are essentially amplifying the effect of perturbing your system, and so then yeah, we want to go to the very large system size, and even for XX spin chain like a 4H site, it's not really conformal field theory as I show the scaling, finite size scaling of the physical spectrum. But if you go to large enough size, spectrum started to be described by the conformal field theory spectrum. So there's always this RG flow. Yeah.
And for 2+1, do you also have the equivalent of the Rindler space and the Unruh effect?
Yes, yes. So that's you can also do. Yes, but for 2+1 decays, obviously there are more choice as to the shape of the subregion A. In 1D, it's pretty much like just the length of the interval. So in higher dimensions, we can also talk about some details about the shape of the regions. But if you limit yourself to disk or ball, the same story applies. Yeah.
Thank you.
More questions? Well, maybe I'll ask one. So could you go back to the slide where you show the different ways of twisting the torus to actually extract the T and S matrices?
Yeah.
Yeah.
Oh. Yeah.
Yeah, that's the one. So I'm actually not seeing the difference between the upper and the lower panels. So what's the difference?
Yeah. Yes, actually, I kind of didn't explain that well. So here and here, yeah.
Yeah.
So yeah, so I think idea is that we start from, let's say we start from this torus.
Right. So this is the space torus.
This is spatial torus,
yeah.
And the way I want to present my torus is to take big space like
right.
plane,
Mm-hmm.
and I identify different points on this plane, and so that's basically specified by lattice vector, which is this and that. So this tau is the something which specifies lattice vector or reciprocal lattice vector or something like that. So I change my tau such that I move this tau from here by 1 unit. Okay, so that's simply saying I start with two lattice vector, but I consider, let's say this is A, B, but instead of A and B, I consider A and A plus B. Mm-hmm. But that's in terms of identification of the original points on the original plane, it gives you the same identification. Right. Right. So this should represent the same torus,
right.
although it looks different.
Right.
So that means if you start from here to here, your Hamiltonian goes back to itself, but state may not. So that's why we get this. Right. Okay, so this is T transformation. S transformation is not the same as this. So I think it's written this way. I effectively changes the role of A and B. That's what I should do.
That's more like a rotation in a way.
It should be like a 90-degree rotation.
I see.
Written this way, it may not be clear because, yeah, so I think this may not be a good way of doing this, but it's just a rotation, 90-degree rotation.
Okay.
Yeah. Yeah.
More questions? Yeah.
You told us about the monotonical property of C function and F function. Could it be interpreted in a more physical way, maybe in terms of degree of freedom, degrees of freedom?
Yeah. So if we somehow say C is related to degrees of freedom, yes, we naturally expect as we go along RG flow, we always decrease the low energy degrees of freedom. But I think, first of all, is C really the measure of degrees of freedom, even away from the critical point? I think it's not entirely clear, so that's why we have to go through this. And of course, it may depend on how you construct analog of C away from the critical point. Yeah. Yeah, I think ultimately it should be. It is more desirable to develop more on this direction. For example, I think this particular proof uses Lorentz invariance, but it's perhaps not necessary. It's maybe just stated just as a property of the strong subadditivity, and so on and so forth. Yeah. Yeah, I'm not sure if this answers your question, but yeah, it's certainly, is there a more physical intuition? Yeah. So let's say if Lorentz invariance is not necessary, I think it boils down to how we have a physical interpretation of a strong subadditivity. That's one thing. And so if we define C function in a proper way, it boils down to the physical interpretation of this, I think. Yeah.
Also, you told us about the fact that to have topological degeneracy, you need non-trivial topology, for instance, torus. But sphere has also non-trivial topology. What do you actually mean by non-trivial topology?
I just mean, yeah, so let's say different topology. So it's topology dependent degeneracy. So as you change the genus of your spatial surface, two-dimensional surface, degeneracy depends on the number of handles.